Welcome back to the MATLAB demonstrations. We'll continue preparing the 3R special arm that we have prepared in the last lecture for force control with few more elements that we'll add. So here we go. So these are the demonstrations. So we'll calculate the robot Jacobian and we'll implement it to the MATLAB embedded code into our Simulink model. We'll do it through otherwise also using robotics toolbox. We'll calculate the Jacobian, we'll test it whether it is correct or it is incorrect so as to put a correct Jacobian model to the actual simulation model when we'll be using this to the force control algorithm. So this Jacobian needs to be verified. This is very important. If you have a customized Jacobian, you are not using a Jacobian toolbox. Okay. Similarly, we'll be developing code, embedded MATLAB code in the MATLAB Simulink environment for gravity compensation torque. We'll be doing it through MATLAB embedded code. Again, we'll be testing it. If we are not using robotics toolbox, we need to do it using MATLAB embedded code, and we'll test it before we actually use it to our force control algorithm. We'll implement environment interaction model that we have discussed earlier in the previous lecture. Same model, we'll be using it here again and we'll test it, and we'll finally test the arm for open loop positioning and for free fall forward dynamics simulation. Okay, so let us continue with the MATLAB environment. So here we go. So we will again pick up the same model that we did earlier. So you just see that. So this is the model. Okay, so from here to here, whole of this block sets we have developed earlier. If you remember, we have a 3R special arm as you have seen it here also. So it is the same one. Okay, we have developed these blocks in the previous lecture. Okay, now additionally we have put few more elements to the joints. First is the actuation thing. So torque is now provided by the input and motion will be computed automatically. So what essentially we are doing here, we are doing forward dynamics. Okay, so torque is provided by the input, motion will be computed automatically and will be sensing for position. Okay, joint position. As the robot moves or it remains stationary, will be continuously tracking its position. Okay, so these two will additionally implement this and this over here. Okay, which can be connected and can be stored. So whatever is the joint angle that we are sensing is converted using PS to Simulink converter, and it will be saved here to the variable named Q1. Okay, that is the joint angle 1. And similarly the input block over here is T1. T1 is the runtime variable which is the outcome of gravity compensation torque. Okay, that torque will put it to the joint. Okay, again we'll be using Simulink to PS converter here, that is physical system. These are the physical systems, so we need to convert the data types here from Simulink to physical system. Okay, so each of the joint I did that. So independent torques are T1, T2 and T3. Those are the outcomes of gravity compensation torque, and the runtime variables for the joint angles are stored in Q1, Q2 and Q3. They become the input to the gravity torque calculation block. So now whole of the robot system is ready with actuation and sensing inputs and outputs. Okay, and rest of the robot remains the same. Now gravity compensation torque can be calculated using different ways. The first one I will discuss here is using robotics toolbox. Okay, so here is your robotics toolbox. You can directly double click here and input gravity torque. Okay, that is included in robotics system toolbox. Manipulator algorithms, if you go, let me just show you. So here is your Simscape. This is your robotics system toolbox. So manipulator algorithm. So get Jacobian, forward dynamics, gravity torque. So here it is. So you can directly drag and drop it here to get the block here. Okay. So this is what I have done it earlier. So I have just shown you. So this also includes gravity of 0, 0 minus 9.8065. So as per our convention, gravity is directed downward, okay, along negative of z axis of the base frame. Okay, so that is the gravity which by default it takes it, and configuration of the robot is continuously taken up by the joint angles, that is Q1, Q2 and Q3. As you can see, it is getting highlighted in the model itself, Q1, Q2 and Q3. That goes input through a mux channel. Okay, mux basically it takes up scalar variables, put it in a vector form. Okay, so you can directly go here and do. This is a standard Simulink block set. Okay, that is a smaller Simulink block set, and by default it has 2 channels. You can increase it to 3 channels here. I am double clicking, entering the variable here, number of inputs as 3, and it becomes like this. Make it little bigger so that it becomes easier connecting the lines. Okay, so yes, this is your mux. Similarly, this gravity compensation block will give you a torque output, that is the joint torque output for a particular pose. Pose is defined by these 3 inputs. Okay, so that joint torque, again I will split them because it comes out as a vector. I will split them using dmux. Okay, that again is a Simulink standard block. Again I will make it to 3. Okay, that way I have done. Okay, so this is it. Okay, now it will take in the vector, split it to scalar variables, that are the joint torques. So T1, T2 and T3, that will finally go to this. You can directly disconnect it from here, or instead of storing in a temporary variable and passing it here, it looks very clean though. Okay, you can directly delete this T1 block, go to and from block, okay, and connect it directly from here to here. In that case, whole of this Simulink scheme becomes too much clumsy because all the wires will go from here to there, okay, for all the 3 joints. So in order to avoid that, make the system very clean, I have stored it in a T1 variable and I have passed it to this. Okay, so now this model is ready as it is. Okay, and it is ready to run. So you can directly try it out for the gravity compensation if it is working or not. Okay, so as soon as I execute it, it will compile and it will get executed. So you see, it is this robot is not no more falling back. Okay, it is not freely becoming a double pendulum kind of. Okay, so it is not oscillating, it is remaining stationary. It remains stationary in its place. These are the gravity, center of gravity location for each of the links. Okay, so initial state here I have defined as, you see, for joint 2 it is minus 30. Okay, for joint 1 it was 0, for joint 3 it is plus 60. That makes the robot configuration, initial configuration, and it is not getting changed, you see. Okay, if I change it again to joint 2, I am making it minus 45, and again here I am making it plus 90. Okay, so again I will run it. You see, it is like this, and it is again stable. It is not falling on its own because you are providing it with the gravitational torque which is necessary to maintain this pose. That is known as gravity compensation torque, that is being applied here. Okay, so that becomes my model. Okay, so I will put it back to some value and that should remain as it is. So this way you can try out with different angles and you can see if it runs. Okay, so this is what is the meaning of gravity compensation torque, and you can use this torque block directly in your force control algorithm. Okay, so this can be used This is the end effector position that remains stationary. It is not getting changed. End effector x, you can plot for all the three end effector x, y and z. Okay, all the plots can be seen. Robot doesn't change its position. Okay, now I'll make this under remark. Okay, I'll put it in comment now. I'll use this torque. This is what? This is my MATLAB coded block which can be inserted from here. This becomes a MATLAB function. Okay, user defined function. So that can be put here. Okay, so you see this is the block, you double click it. So this is the default function. So y1, y is the output from this function. You can put it in vector form as y1 and y2. Similarly, input could be u1 and u2. Okay, in that case you can return y as y1 is equal to some value. I'll just demonstrate it using y2 is equal to u2. I am just taking in the value and returning it out. You can have a predefined function for input and output here. Okay, u1 and u2 is taken here. Okay, now if you go back and see, it can now take up two inputs, u1 and u2, give you two outputs, y1 and y2. So this is how you define a MATLAB function. Okay, that is embedded code. You can put it the way you code it in MATLAB, you can put all those here. So using that, I have defined this gravity torque vector here. Okay, it will take in all the joint angles q1, q2 and q3 and give you tau 1, tau 2 and tau 3. Okay, tau 3. Those are directly connected here. Okay, let us now peek in here what is inside. So I'll double click here. I'll enlarge it a bit so that it becomes very clear. So I have put the masses here. That is mass for the first link, second link and third link. First link is not getting affected by the gravity because it is perpendicular to the ground. Okay, so it is not getting, so that is not coming into picture. So if you see your gravity torque, how was that? It is like this. So it is exactly like this. So you see you have 0, that is tau g. For tau 1 is 0, tau 2 is this, tau 3 is this. They all depend on link lengths A2, A3 and joint angle theta 2 and theta 3. Okay, so it is independent of joint angle theta 1 again because the first link you see it is perpendicular to the ground and gravity is directed like this. Okay, so this is my gravity compensation torque. Exactly this I have coded it inside. Okay, and taking care of the sign of the torque. Okay, torque positive is like this. So this is your tau 2, this is your tau 3. If this gives you in plus, maybe it is in minus. You need to take care how you have put your axis. In my case, I have put the axis like this, but in the MATLAB it may be different. So take care of that and put the signs correctly. Okay, that is what I have done. So I have exactly inserted the masses. Masses you can directly get it from here, link mass. Okay, inertia properties, you get the mass from here. Okay, density and the mass. So if you just go back to custom, it shows you the mass. Okay, so exactly this one you can take it and put it here. Okay, m2 and m3, g is the acceleration due to gravity that I have taken. Link lengths are a2 and a3, those are here. This is exactly what I have shown you over here. Okay, exactly this torque is coded here in the MATLAB fashion. So input variables are joint angles q1, q2 and q3. Output variables are t1, t2 and t3. Okay, that is passed through this. Okay, now let us see how does it work. Okay, okay, this is again stable. Initial state was whatever is the initial state. Accordingly, my function calculated the joint torques and fed it to the robot joints, and the robot is stationary in its place. Now let me try something. If I put G is equal to 0 here, okay. So if gravity is 0, this should behave accordingly, right? So in this case, I am in the code assuming gravity is equal to 0. So this should give me an output torque which is equal to 0 because all these contains G. So all the torques are 0. So that means it is no longer supporting the links in its place. So it should fall on its own. Okay. So as soon as I compile it, it falls like a pendulum. You saw that? So this is how it will freely swing and it will do this motion. Got it? These are the link mass location. So this gravity compensation, as soon as I activate it once again, it will come into action. Okay. So I'll put it back the way it was. So I have taken 9. You can make it go on the Mars. If you take gravity as 9.81 by 6, so it is gravity I am assuming that is 9.81 by 6, that is on maybe moon or somewhere. Okay. So you can change the acceleration due to gravity here, accordingly it will support. And now if I run it, so it behaves little different. It falls but not that fast because it is getting compensated a bit, not completely. Okay. So that becomes my gravity compensation torque. So this is the physical significance of having a gravity compensation torque. So it makes you feel as if there is no gravity at all. Okay. So as long as you keep on compensating it, the robot behaves equally in all the directions. So robot comes to space. Okay. So this is gravity compensation. So I'll leave it in remark. I won't be using this from the robotics toolbox. Rather, I will be using gravity torque that I have coded it myself. At least for 3 link, it is very, very simple. But for links greater than 3, so you may have gravity compensation torque which is calculated using ready-made toolbox, which is robotic system toolbox. You can use gravity torque block. Okay, but for my case, I am keeping it as it is. So this is gravity compensation. So I have designed it. I have designed it using MATLAB toolbox. I have designed it using robotics toolbox, MATLAB embedded code, and I have tried them both. Now I'll move ahead with the robot Jacobian. Okay. So I'll do the Jacobian calculation once again. Okay. So gravity is over. I won't play with this anymore. Okay. Now I have coded the Jacobian. Okay. Inside this again I have taken input as Q1, Q2 and Q3. Those are the joint angles. You know Jacobian is a function of joint angles. If you see here, so it takes in the joint angles, link length. Okay. So Jacobian. So this exactly this is coded here. Okay. So you have all the elements visible here as J11, J12, J13. So all the elements as it is there here. So exactly these elements are coded here. I am returning that as a matrix here. Okay. I am clubbing all J11, 12, 13. Next row is J21, 22, 23. Next row is J31, 32 and 33. Again I am considering the signs which should be properly put. That is the reason when you code, you need to check, you need to cross verify your joint angle direction, axis direction. Accordingly, you need to do some changes and needs to be verified. Okay. So this is your gravity compensation. Okay. Now let me check. How will you check it? So in order to check that, what I will do, I remember my equation for Jacobian. What it does basically, you can directly use the equation J theta dot is equal to end effector velocity. So this is the standard equation that I will be using. So I will directly take input from the joints and multiply with the Jacobian, and I will obtain the x dots, all the end effector velocity. End effector velocity I can also obtain using the end effector transformation block. Okay, transform sensor here, and you know I can directly obtain the velocities from here. So velocities can be obtained, velocity along x, velocity along y, velocity along z, all the three can be obtained. Okay, and I'll compare that. I'll store it first, I'll plot it here, end effector velocity from the MATLAB. Okay, that is using the transform sensor. I'll plot it here. Okay, so I have used PS to Simulink converter for all the velocities which comes from physical system, converted it to Simulink and clubbed them together and plotted it in a single plot scope. Okay, now again I have again used the joint angles here, Q1 dot, Q2 dot, Q3 dot. So those are the additional output. Now I have taken it from here. So all the joints are not only sensing the position, it is also sensing the joint angular velocity also. So that velocity again is saved as Q1 dot, Q2 dot, okay, Q1 dot here, Q2 dot here and Q3 dot here. So those are input here, converted it to the vector form, multiplied with the Jacobian that I have obtained through my MATLAB. Okay, and I have obtained end effector velocity using Jacobian. So using Jacobian I have calculated the end effector velocity, and using the MATLAB transform sensor I have calculated the velocity. Both should match, and that will verify my Jacobian if it is correct or it is incorrect. Okay, so let me run this. Okay, now it is stationary, so it is not moving. What I should be doing here, I'll make the gravity equal to 0 so that it falls, so as to see some changes in the end effector velocity. So I'll just remove my gravity compensation here. I'll make G is equal to 0. Okay, G is equal to 0 so that it falls on its own. There is no supporting gravity compensation torque, so it will fall. Okay, it falls like this. Okay, as soon as the simulation is over, I'll check for the plots if they are coming correct or not. Okay, so this is how it has executed. Now I'll check the plots. End effector velocity from MATLAB is this. Okay, end effector velocity from my own calculation is this. Okay, so these are the two plots. You see both are exactly the same. End effector velocity from MATLAB and end effector velocity from my own Jacobian. Both the velocity along x, velocity along y are plotted, and they are perfectly matching. That means my Jacobian is correct. So you must have noticed I have done some changes to my Jacobian calculation. Okay, I have put some positive and negative signs accordingly. You see I have put negative, negative and negative here, because that joint angle was not at the axis how I have calculated my Jacobian analytically. So while putting it here, you have to check your axis direction before you actually put it here, then only it will match. Okay, so you need to do those changes. Okay, so those changes were done here and I have found it correct. So this is the way you can verify, and end effector velocity can also be obtained in multiple number of ways. You can directly check the displacement, take derivative and get velocity along x. Similarly, velocity along z. So you can directly take the value here, take derivative and find out the velocity. Okay, that is another way of calculating velocity. This way you can directly obtain the velocity, or you can obtain using your Jacobian. So that way you validate your Jacobian. So validation of Jacobian is done. Again, you can directly use robotic system toolbox to get the Jacobian. Okay, so in robotic system toolbox, you double click here, go to Jacobian, and you can directly get the toolbox called as get Jacobian. Okay, this uses the rigid body tree as it is written here. So you need to execute same in case of gravity also. It uses the rigid body tree, and you know already how we can import that here. So I'll call it as tree link is equal to import robot. In quotes, I have taken the model name as 3link.slx. So when you do this, you can directly import that as an object in your workspace. So that has to be included here. So when you do it here, you write three-link, okay, three-link here, and this becomes complete. So now it can take in the configuration as you have taken it in your Jacobian. Okay, this is how it is used. Okay, so I have already done it for you. I'll uncomment this, and this makes my Jacobian using robotics toolbox. It is shown as red because you cannot save same variable from two different sources. Okay, so you have to make one of them in remark. If you put this in comment, so this becomes okay. So this is how you can calculate Jacobian using robotic system toolbox. But I'll be using, as because it is a 3-link manipulator, so it is very simple. I'll be using my own block that I have made using this code. Okay, so just like gravity block, it can be used from robotic system toolbox. Even Jacobian can be used. Okay, but I am not going to use this for my future calculations and other force simulation. Okay, so I'll stick to this gravity and this Jacobian strictly. Now I'll do create the environment so as to create a plane which moves towards the robot and does something. This is what is I wanted to do. Okay, so you see there is a plane which moves towards the static robot, and I'll see if this plane makes my robot flex or not. Okay, upon interaction it should become soft, or it should behave like a spring. Okay, so that collision is detected using environment modeling. As you have seen, F is equal to Ke into x minus xc. X is the end effector position of the robot. This is your x. Xc is the position of this moving obstacle. Okay, when this collides with the robot, so there is difference in position. Okay, it moves towards the robot. So wherever you have commanded your robot to go, it gets into the robot's position and robot penetrates into that object. So if there is any penetration, so and because of stiffness of this object which is there, okay, it creates a force, okay, a normal surface normal force which will actually resist the robot to getting into this surface. Okay, so this is my model. So what I have done here is x minus xc into Ke should give me the force vector. Okay, I have ignored any frictional forces along the wall surfaces. I have just considered the normal forces which will come out of this moving obstacle. So this is my environment. I want to code in to my MATLAB Simulink environment. So this is my model. Okay, now I am ready with everything. I am ready with gravity torque. I am ready with Jacobian. I have already validated my Jacobian and the gravity torque. Okay, so this is my 3R robot which we have done already. So now I need to create a moving obstacle. How to do that? Basically, what I have done here is with the same world frame, I have created a different system here. Okay, so basically this is your rigid body transform. I am first making a frame which is in space about which this obstacle will move. So this is that stationary frame. This is situated in the robot workspace somewhere. So I have done that transformation along z axis. Some translation offset I have put here. I have kept that at 2 meter. I know my link lengths are second link and third link is 1 meter and 1 meter. So in any case, this should start from a position which is greater than 2 meter and start moving towards the robot. So that offset is there. That becomes the base of this moving obstacle. Okay, so this is my rigid body transform. This is a brick solid element, a small element of some density, doesn't matter. It's a very small reference frame which is located at that location, x is equal to 2 meter, 0 and 0, okay, and this is of negligible dimensions, that is not very important. Now I have put a prismatic joint. Prismatic joint actually will make this robot move towards the object, okay. So now you have frames here again, this is the frame is put like this because I want to move along this direction, okay. Negative of x axis should be my new z axis, as you know, because my robot is directed along the forward x axis. So because I want my obstacle to move along this direction, so this is my reference frame, F2 is my reference frame now. So about F2 I will have a moving object which moves about F2 along this direction, that is negative x axis, okay. So that is my this. So this is your prismatic joint, this will be aligned along negative of x axis, okay, and this is your moving obstacle, nothing but it is like a plane, okay, this plane, okay. Mass doesn't matter, but it has some geometry of 1 meter into 1 meter, okay, and negligible thickness of 0.005 meter. So that is how I have taken and did nothing, okay. I will connect this to the as a follower to the prismatic joint, okay. So this is my obstacle. So now this obstacle should move with time. How? This is a value that I am taking in. So this is the clock function. This simply creates a clock ticks corresponding to the simulation time. So this is the clock tick generator, and this is the function block, okay. Function block, if you just type FCN, this is the user defined function block which can take in some value and gives you output depending on the function that you define here, okay. So now I have taken in the clock input, V is equal to, so I have kept it as velocity into the time. So this becomes my velocity. Velocity is 0.05 meter per second and time is the input to this function block, okay, velocity into time. So this will create a uniformly moving system, obstacle towards the robot, okay. Let us see how it behaves, then you will understand it more closely, okay. Okay, so you see it is moving at a, so this is my stationary frame which is here, okay, about which this obstacle is moving towards the robot at a velocity of 0.05 meter per second towards the robot. Over here it is velocity into time, displacement is equal to velocity into time, that is what I have taken here. This is simple equation that becomes my function, fed it to the prismatic joint with the actuation as motion provided by the input, okay, and force is automatically computed, that is irrelevant here. I just want to move it, okay. So now the position of the wall is continuously monitored using a transform sensor. It is doing forward kinematics for this moving obstacle with respect to base, what is my current location, okay. So same frame I have connected as a follower, this is the base, this will give me the displacement along x axis. I have stored that here as a environment position block and I have plotted it here also. You see it was moving with time, okay. It moves continuously starting from the location 2 0 0, x is equal to 2 0 0 and moving with the constant velocity of 0.05 meter per second. Displacement is continuously towards the robot, okay. Okay, so this is how this moving obstacle is created. This will be used for simulation only, okay. It has got nothing to do with force control algorithm here. So I am saving the environment position, I am saving the robot position. So using these two, I will be calculating the error and I will multiply with stiffness matrix of the environment to generate the forces that comes on the robot tip when it interacts with the wall. Currently, as because there is no interaction model, this robot is in its position, it is not getting deflected and it penetrates through the wall. Okay, so this is it. Okay. So now moving wall is created. I have saved environment position and the robot position. I will try to create the environment interaction model. Okay. So it is environment interaction model. Okay. So this time, this is my interaction model. It takes in the input of the robot's end effector position, that comes from here, and the environment position that comes from the wall location. Moving wall, it was moving towards the robot. So I am saving both the positions. I am inserting it here. Essentially, I am going to code in this equation here using Simulink blocks. So I will take the robot's position, I will take the environment position, take the difference, multiply with stiffness matrix, okay, diagonal stiffness matrix of the moving obstacle, and it will generate the force. Okay, let us see how I have implemented it in my blocks. So this is my block. Okay, so robot position comes from here, environment position comes from here. I am taking the difference and multiplying with environment is stiffness to calculate the force. Force comes out when the robot actually gets into the wall. Okay, so robot position and environment position, when it is having some positive value, that means it has penetrated into the wall. In that case, this is a enabled system. These blocks you can find it in your MATLAB Simulink, because these are all Simulink blocks, nothing to do with robotics toolbox or Simscape SimMechanics block. Okay, so this will give you an output of reaction force. Force is calculated only when the robot penetrates into the wall. Okay, otherwise when there is no contact, force should not be calculated and it becomes equal to 0. So that job is being done over here. Now I am calculating whether the contact is happening or it is not happening. So contact on and contact off is passed through this if then else block. They are merged to a single output. So this contact on or off will be given by this environment interaction block. Okay, so now let us run this once again. So this is my interaction model. So this should give me the reaction force as well as contact on and off situation, okay, status of that. So if I run this, so as soon as it establishes contact, it won't deflect the robot still because I haven't applied any force control algorithm here. Okay, but it should give me the force. So it is moving towards the robot. So you see what it is giving. It was giving 0 force, 0 force, 0 force up till here when the contact actually happened, and gradually it has calculated the force. So gradually it is increasing because it is continuously moving into the wall. Okay, robot gets into that. Okay, as the robot gets into the wall, force is getting calculated and continuously increased because it is getting penetrated more and more. Okay, and this is the situation of contact. So contact has happened over here, it gave 1. So this block will be used as an interaction block. Other blocks we have already designed and we have verified them, Jacobian and Gravity-Torque. So now we are ready for any force control algorithm to be developed over this. So I have created the moving obstacle also. So what all things that I have demonstrated now, I have calculated and tested the robot Jacobian using MATLAB embedded code. This is what we will be using, and we also did using robotics toolbox. We won't be using this. calculated and tested the gravity compensation torque using MATLAB embedded code and robotics toolbox. Again, I will be using this. We have implemented environment interaction model to do any force calculation and implement any force control algorithm on top of that. Okay, I have checked the robot for open loop positioning, and also we have seen free fall under dynamic simulation, forward dynamic simulation. We have just removed the gravity compensation torque and we saw the robot was falling on its own, that is with the zero torque at the input. Okay, how the robot behaves. Okay, so that is what was the forward dynamic simulation of 3R spatial manipulator we have done. So in the next lecture I will discuss hybrid and stiffness force controller. That's all for this lecture. Thanks a lot.